All right, guys, what's going on? I'm going to be absent tomorrow / today, depending on what time you're watching this video. So we're going to continue the notes, and if you need to watch something over again, you can just rewind it, check it out. We're going to be working with our calculators today. Make sure you have your calculators. We're going to be working with the z tables. Make sure you have your z table. Okay, so let's just do this last example. I don't think we quite finished it today. Okay, so we need to find the area between these two. So let's first write it out, or I should say sketch it. So we're looking for the area between 1.62 and negative 1.35. So we're looking for this area here. The z table actually doesn't give you that kind of area. It only gives you area which accumulates from the left. So what I want to do is write a subtraction like this, where we find the area to the left, 1.62, and then from that, I'm going to subtract the area to the left of negative 1.35. And that'll give me that middle area, right? So let's write out the notation now. This is the probability that x is between, I should say that z is between negative 1.35 and 1.62. That's equal to the probability that z is less than 1.62 minus the probability that z is less than negative 1.35. So I'm sorry if we did this already. You could just fast forward. All right. So what are these values? Let's go look them up. So 1.62. Where's 1.0? Where's my z table? Okay, so 1.62, 1.6, 2.9474. Okay, let's find the area for negative 1.35. Negatives are on the next page. Negative 1.35. So that's 0, 1, 2, 3, 4, 5. So 0.0885. All right, so I have to subtract these two numbers from each other. I'll use my calculator since I can't really do this sort of thing in my head reliably. I don't want to mess you guys up. It's one thing if I have you guys checking me, but okay, and I get 0.8589. All right, very good. A normal probability distribution curve can also be used as a probability distribution curve for normally distributed values. This is just a fancy way of saying area, probability, and percent are all the same thing for the standard normal distribution. Find the probability for each using a standard normal distribution. Okay, I think at this point, maybe we'll do a couple more of the z tables, and then maybe on this last one, I will go ahead and show you how to use your calculator. All right, so we want the values between 0 and 2.35. So let's sketch it out. Okay, there's my 0 and 2.53. Well, this is actually pretty straightforward because how much is below 0.5, right? Well, first of all, we should probably find the area on the right-hand side here, 2.53. So I'll find that area, and then I'll subtract from that area the 0. But I already know this second one, right? You should too. So let's go find the area to the left of 2.53. Let's make sure no one's here. Yeah, 2.53. 0, 1, 2, 3. So 0.9943. Geez, almost all of the population. And then how much is to the left of 0? 50. Right? So you guys remember that. 0.5. This one I might actually be able to do in my head. So that's going to be 0.4943. Cool. This one's straightforward from the table. I'm going to go ahead and I think I have to change this to something here and make it a little bit better for you. Huh. I thought that I had an option here. I guess not. I thought I had like a visual. Make it go to. Guess not. Optimize for video, I think is like the option I'm looking for. Sorry to waste you guys' time. It's usually right there. Anyway, matters not. All right, so we're looking for the probability to the left of negative 1.26. That area right there. So that's actually, direct problem. So looking at the Z table, what do you find? 0, 1, 2, 3, 4, 5, 6. So 0.1038. That's your answer for that one. I swear, it's just bothering me when I know how to do something, but it's just not letting me. Or I just can't see. Whatever. Okay. So let's use the calculator for this. I know a lot of you guys don't like using a calculator, but it really is super helpful, especially when it comes to these sorts of things, instead of using the table. So let's go ahead and let's use that calculator. So greater than 1.98. So let me show you how to do this. We're going to go to menu. You're going to go to statistics, distributions. We are in the normal distribution. We want a normal CDF. CDF stands for cumulative distribution function. Now I have these inputs. Now why is this set to 0 and 1? Because it's set to the standard normal distribution as a default. We can always change those, but we're not going to this time. So the lower bound in this case, I want to be greater than 1.98. Okay, so my lower bound is 1.98. Our upper bound is actually positive infinity. We have that button, I think, right here. Oh, I lied. Maybe not. Maybe it's over here. And that one's just not working at all. Guess I froze it. Okay, let's try that one more time. You don't have to use infinity if you don't want to, but it should work. Come on. I think next time I'll just type in like 1,000,000 or something. All right, it's not working for me. It'll probably work for you. Oh, there it is. I don't want to do that. Oh, jeez. Oh, sorry, guys. It's not my fault. I swear to God. Okay. Okay. How about that? That'll be just as good. So our answer is 0.0238, or no, 339. Fine with me. And it makes sense. You know, it's not like astronomically small or astronomically big. It's right in the ballpark. So sometimes one must find a specific z-value for a given area under the standard normal distribution curve. The procedure is to work backwards. So we're actually going to just jump to the calculator now, even though you could use the table for this as well. It's not hard to do. You just have to look up for 0.7123. Okay, so I might as well just look at it since we have it right here. So 0.7123. Where's 0.71? 0.71. Okay, looks like that'd be 0.56. So z is equal to 0.56. See that? 0.56. All right, now let's use our calculators. So we were going to use an inverse norm CDF because we're going backwards, right? Statistics, distributions, inverse normal, right there. Now this really does only work from the left, okay? So the area here from the left is 70, we'll have to put it in decimals, 0.7123. All right, this is standard normal. We are looking for the z. Here we go, 0.56. So z is equal to 0.56. Find the z-value such that 19.77% of the area in the standard normal distribution lies to the right. Okay, so for this, I have to think about it a little bit more. So what's 1 minus 0.1977? Actually, probably need some help with that. I'm not smart like you guys. 0.8023. Okay, so I'm just going to go ahead and copy this. So let's go through the whole menu thing again. You can, of course, it will always work. And this time I'm putting in 0.8023. Still standard normal, 0 and 1. We get an answer of 0.8498. So that's the z value. Okay. All right. Example 9. Find the z-values for the middle 80% of the standard normal distribution. Okay, so that's 0. We are looking for, what are these z-values such that this is 0.8. Well, if that's 0.8, then what is on the left? What is on the right? Together, they have to add up to 0.2. But that's symmetrical, remember? So 0.2 divided by 2 is 0.1. So this must be 0.1. So if I'm summing from the left, what is that going to be? 0.1 plus 0.8, right? So 0.9. So this z value will correspond to an area of 0.9, and this z value will correspond to an area of 0.1. Okay, so 0.9 and 0.1. I can use the table for that probably quicker than I can the calculator. Where's 0.9? Well, I'm not going to get exact values here, so might as well use the calculator. Okay, so inverse norm. Point 0.9, 1, 2, 3, 4. I get, we'll call this one here. Call that Z1, we'll call this Z2. So Z2 is equal to 1.28. We'll call Z1, the one on the left-hand side, that would correspond with an area of 0.1. Two decimal places, geez. All right, so that's negative. Of course it's going to be symmetrical. Silly me. Why did I go through all that work? Look, they're going to be symmetrical because it's about the center. So same distance from the center. Easy peasy. Okay, still inverse, right? If you're looking for Z, it's the inverse. So 54.78% of the area under the distribution curve lies to the left. Okay, so draw your curve. We're looking for 0.54, so that's going to be a little bit more than half, right? So this area is 0.5478. What corresponds to that? Let's use the table, probably easier. 5478, 5478. There it is, 0.12. Okay. 69.85% of the area lies, you know, we just did these exactly like it. So why don't you do those on your own? B and C. We just did those exactly like it. And, you know, you can use your calculator, or you can, remember, if it lies to the right, you're going to have to do that 1 minus the complement. Okay? And you're going to have to look for that value. Same thing here. So heads up with that. And, well, I want you guys to do it. So try it on your own, and then like pause the video, and then you come back and look at the answers. I'll give you the answers now. We'll work it out. Okay, so 0.6985, 1 minus 0.6985, 1 minus 0.6985. That's 0.3015. So what z value corresponds with 0.3015? Wait. That makes sense. Yeah. Okay. So z is negative 0.52 for that one. Okay. Let's not get away from sketching it. I did for a second there. So they want 11.9% to be to the right, which means what must be to the left? 1 minus 0.119. That's 0.881. So looking for the z value that corresponds to that. Okay, so that z is 1.18. Hopefully you guys did that well. Okay. And remember, a lot of things behave normally. And that includes a lot of stuff. So if you can make these sorts of calculations, you can then find like size of the population, then get like a raw count. It's pretty cool stuff. All right, guys. It can help you make claims like, "Oh, this is way too big to be considered to be normal," or something like that. This is way too small to be considered normal. Why are we talking about this when it's such a small percentage? You know, blah blah blah. It keeps things keeps things normal. Anyway, that's that. Do your Alex, and we'll move on to the next section here. Have a great day, guys.